Hello students, this video is specially designed for all the students of NEET as well as JEE with respect to thermodynamics, a very important chapter, a quick snapshot of what the chapter is about, and some shortcuts with respect to JEE and NEET, how to memorize the same. Alright, so here we go, we'll start with this. First of all, what exactly is thermodynamics, people? Now when I'm talking about thermodynamics, then thermodynamics, that's a branch of physical chemistry that deals with the conversion of one form of energy into or transforms one form of energy into another form of energy. Like various examples we have. For example, process of electrolysis. In process of electrolysis, there is conversion of nothing but what we can call as electrical energy is converted into chemical energy. Same way, if I'm talking about a working of a car battery or a working of a lead accumulator, it's nothing but conversion of chemical energy into electrical energy. So that's thermodynamics, what we have. Now in thermodynamics, we have first of all something called as a system. What exactly is a system? System, a specific portion of the universe which is under thermodynamic consideration. And apart from the system, whatever is the remaining part is our surrounding, and system plus surrounding constitutes our entire universe. Now, who separates the system from the surrounding? There is a boundary, an imaginary boundary or a real surface which separates the system from the surroundings. So we say, depending on the boundary, we say systems can be of three types. What are they? Open system, closed system, and an isolated system. Have a look at the presentation, please. So first we have an open system. Second we have that's a closed system. And third we have that's an isolated system. Open system, system capable of exchanging energy and matter with the surroundings. Like a cup of hot coffee will lose energy to the surroundings, as well as there'll be some amount of matter that also will get exchanged. Basically, all living things are going to be examples of open system. Closed system, system which is capable of exchanging only energy and not matter with the surrounding. Then such a system is called as a closed system. Like anything in a closed vessel, is this clear? Like a cup of coffee on which I keep a coaster, then it's going to only exchange energy with the surrounding. The volume of that coffee will remain the same. That's an closed system. Third, we have isolated system. Isolated system which is capable of exchanging neither matter nor energy with the surroundings. Example, universe. Universe is infinite. So we say our galaxy systems, what we have, it's behaving as an isolated system. There is no exchange of energy or matter with its surroundings. Or like a coffee in a thermos flask. Thermos flask more clearly cannot be called as a isolated system. It's a thermally insulated system. Means we regulate the temperature so that for whatever time, 2 hours, 4 hours, depending on the insulation, or maybe 8 hours, that cup of coffee will remain hot in a thermos flask, but eventually after a stipulated time, it will come down to room temperature. So that's an isolated system. So depending on boundary, three types of system: open system, closed system, and an isolated system. Next, now we have properties. Two properties to discuss. One is what we call as an intensive property, and one what we call as an extensive property. What's the difference between the two? I for intensive, I for independent. Properties which are independent of the amount of substance present are called intensive properties. Extensive properties, properties which will depend on the amount of substance present. If the amount of substance will change, that property will also change. Like mass, is this clear? Volume, they will depend on the amount of substance present. So those are called extensive property. Intensive property, like boiling point. I take 1 ml, I take 10 ml, I take 100 ml, I take 500 ml. The boiling point of water will remain the same. That's 373 Kelvin. So boiling point is an intensive property. It's independent of the amount of substance. Clear? That's one. So here are the examples. Intensive, all of them: temperature, pressure, concentration, density, viscosity, refractive index, surface tension, melting point, boiling point, molar rate capacity, P of H of a given solution, specific heat. All these are intensive. They are independent because specific heat is only for 1 gram. Molar rate capacity is for 1 mole of a substance, that way. And extensive properties, that will depend. Like examples: mass, volume, then we have energy, work, internal energy, enthalpy, entropy, area. All these are extensive property. Just an idea to you, a shortcut to remember over here: ratio of two extensive property will always be an intensive property. Like density is mass by volume. So mass and volume both are extensive, density is intensive. One more example with respect to solutions: mole fraction. What's the definition of mole fraction? Number of moles of one component, solute or solvent, upon total number of moles of the solution. So here number of moles is given mass upon molar mass. So that depends on the amount of substance. Whereas if I say total number of moles, yes, that will also depend upon the amount. But mole fraction is always going to be an intensive property. So ratio of two extensive is always an intensive property. Then next we have thermodynamic equilibrium. What's a thermodynamic equilibrium? Our equilibrium, people, is basically nothing but when we say, first of all, we have a state of a system. State means we measure the properties, the measurable ones, the macroscopic properties: pressure, volume, temperature, the chemical composition. All these are the measurable properties that defines the state of a system. Now with respect to the state, when I say thermodynamic equilibrium, meaning we will say all these macroscopic properties, one of the variables, it is clear, at a time will remain constant. Like for example, if I say a system is under, there are three types of what I can call as thermodynamic equilibrium. Thermal equilibrium: temperature remains constant with time. Mechanical equilibrium: pressure remains constant with time. Chemical equilibrium: the chemical composition remains constant with time. So when the existence of these three equilibria are there simultaneously, that's what we call as a thermodynamic equilibrium. So we have these variables, that is the pressure, volume, temperature, they will remain constant. Then we have people more to talk process. What's a process? Process is basically a path, or what we can say, a path by which transformation takes place. So this process where transformation takes place of one substance into another, or one reactant into another product, then that's what we call as nothing but a process. These processes are of different types. First to start, isothermal process. Iso, similar, thermal, temperature, which means constant temperature. So when the temperature of the system remains constant, that process is called isothermal process. Now in isothermal process, what is happening? Exchange of heat takes place between the system and the surrounding to keep its own temperature constant. Alright, that's one. So expansion will take place, a gas will expand by absorption of heat, and contraction will take place by giving away of heat. So we say internal energy remains constant. What is internal energy? It is also one of the thermodynamic functions. Internal energy is also called intrinsic energy. We will see it ahead. It is the energy by virtue of its kinetic and potential energy. So as internal energy is nothing but a summation of kinetic and potential, kinetic energy is temperature dependent. So internal energy is clear, is nothing but a function of temperature. So if temperature is constant, then change in internal energy is 0. Enthalpy change delta H is also 0. Alright, enthalpy is the heat content, but delta H is 0 only for an ideal gas. Now what is this I have written over here? Q is equal to minus W, or W is equal to minus Q. We're just going to do in the next 1 or 2 slides the first law of thermodynamics, that is delta U is equal to Q plus W. Delta U, the change in internal energy, Q is the amount of heat exchange, and W is the work done. So if the process is isothermal, its internal energy is constant, so delta U is 0. So if delta U is 0, we can write Q as minus W or W as minus Q. That's one. Second, we have adiabatic process. What's an adiabatic process? Process where no heat is allowed to enter nor leave the system. The total heat content, there's no exchange of heat between the system and the surroundings, so the variable Q is 0. There's whatever is the enthalpy change will take place within the system itself. Like in adiabatic process, when a gas expands, it takes away, the work is done at the expense of its own internal energy. So it takes away whatever heat is available within the system. So that's why its own temperature falls. Like a working of a DO bottle. When you spray DO on your body, the bottle becomes cold. Why? Adiabatic expansion. The liquid inside will try to expand, so it takes away whatever air is there inside. It takes away the heat from there. Its own temperature falls. That's one. So adiabatic process, Q is 0. So if there is Q 0, delta U, delta T. Now this delta U, delta T and delta H are not 0 because we say there are enthalpy changes within the system. Now coming back to the first law, delta U is Q plus W. So in adiabatic, if Q is 0, delta U is W. That's the expression we have. Then isochoric process. What is the meaning of the word isochoric? Isochore means volume remains constant. Basically in a closed vessels where the volume remains constant, then such processes are called isochoric process, where if the volume remains constant over there, people, the variable delta V is 0. How can work done be 0? Work done is 0 because we will see this now after the first law. Work done in pressure volume type. So for PV type of work, we say W is minus P delta V. So if the volume, if the volume is constant, the change in volume delta V is 0. So if delta V is 0, work done is also 0 over there. And what do you mean by this final part? QV is equal to delta U Q. Now formula again, delta U is Q plus W, first law of thermodynamics. Now volume is constant, so delta V is 0. So work done, P delta V is also 0. So Q is equal to delta U. And I'm writing V as the subscript, which means the heat exchanged at constant volume is nothing but change in internal energy. Okay. Secondly, the last process to talk here, that's isobaric process. What's an isobaric? Isobar. Bar is the unit of pressure, right? 1 atmosphere is 1 bar. So iso, constant pressure, that's isobaric. Now if the pressure is constant, people, first law of thermodynamics is intact. Delta U is Q plus W. Now work done W is minus P external delta V. So if I take QP on one side, if you see the slide, QP is delta U plus P external delta V. And this is also the expression for delta H. Delta H, that's also called enthalpy change, or we write it as QP, that is the amount of heat exchanged at constant pressure. So the heat exchange at constant pressure is nothing but change in enthalpy. So whenever you come across the two variables, heat of reaction at constant pressure, the variable is QP, that's delta H. Heat of reaction at constant volume, the variable is QV, that's delta U. Then next to talk, now we have to talk about state function. I told you what exactly is a state, what do you call as a state of a system, where we define the measurable properties. Now what is a state function? A property whose value will only depend on its initial state and the final state, but not on the path followed to bring about the change. Then such a process or such a system or such a state is what we call as a state function. Pressure, volume, temperature, internal energy, enthalpy, entropy, Gibbs free energy, all are state function. Means their value will only depend on the initial state and the final state. Let's start with a very simple example. Okay. Suppose in a classroom I'm sitting on desk number 1 and there is a student sitting on desk number 10. Now from desk number 1, I say that's my state A. Matlab, the student sitting on desk 1, I'm measuring the properties. Pressure is P1, volume is V1, temperature is T1. If I alter one of the variables, any one of them, pressure, volume or temperature, I get a new state, that is the student sitting on the 10th bench. There I have new set of variables, pressure becomes P2, volume is T2 and temperature is T2. Now thermodynamics says whether I go from A to B or if I go from B to A, the magnitude will remain the same, only it will have an opposite sign. Then such properties are termed as state function. Means in other words, going from A to B, there are how many paths? Infinite number of paths. Like I can just walk from desk 1 to desk 10, or I can just jump on the desk 1 to and go to the 10th desk, or from, you know what I can say, desk 1 over there. Is this clear? If I have tied a rope over there, I can just swing from the first bench and go to the 10th bench. So irrespective of any path I take, what will be observed? A to B, the difference is going to be delta P, that's say change in pressure. So delta P is P2 minus P1, and back from B to A, it is by infinite number of path, delta P will be P1 minus P2. So irrespective of any path I take, suppose going from A to B, delta P is the magnitude, and coming back from B to A, that magnitude is delta P dash. So delta P is equal to minus delta P dash. Both will have the same magnitude, only it will have an opposite sign. So those are termed as state function. But there are certain properties which depend on the path followed. Those are termed as path functions, like amount of heat exchanged, that's Q. The work done, W. They always will depend on the number of path, hence they are path functions. So that's one. Then next we have people is a reversible process and an irreversible process. Now this is very simple to understand. We have two forces to talk, a driving force and an opposing force. Let's make it simple. I have water flowing down the hill. So what's the driving force? The force by which the water is falling down. That's called the driving force. What's the opposing force? The force by which the same water is splashing upwards. If the difference between the driving force and the opposing force differs by a very, very, very large magnitude, so large that the process cannot be reversed, such a process is called irreversible process. Like for example, we will say water flowing down the hill. Water always flows down the hill only. Water can't be flowing up the hill. All right. That is basically an external work which we have to do if we want to do that. So irreversible processes are all natural processes in which we say the difference between the driving force and the opposing force will differ by a very large magnitude. So much that the opposing force is almost negligible. All right. That's irreversible. Reversible process is a hypothetical process. It's a process which has to be arranged. Let's give a very simple example. A bicycle pump. When I pump the bicycle down, is this clear? What happens? That piston comes down. So when the piston comes down, the gas molecules are going to get contracted, and when I leave the piston, the gas expands and it moves upward by a height h, and it stops. In a reversible process, what is happening now? Now once it comes, when the piston comes up and stops at an height h, matlab an equilibrium is formed between the driving force and the opposing force. Now if the opposing force, that is the gas inside, will expand a little bit more, then what's going to happen, people? Again, now what's going to happen, people, over here? The gas, if the gas expands, the piston will rise little bit upwards. Again, an equilibrium will form between the driving force and the opposing force. Again, the opposing force will increase by a very, very small amount, infinitesimally small amount. Again, the piston will move upwards. And like that, people, in n number of steps, maybe it's infinite number of steps, the piston will displace 100% upwards. So this work done in large number of steps, where at every step there is an equilibrium between the driving force and the opposing force, we say the work done is maximum, what we call as W max. So for W max, two conditions put into your head. Process should be isothermal, temperature constant, and it should be reversible. So reversible definition, there is a very small, infinitesimal small difference between the driving force and the opposing force, such that we say the process can be reversed by increasing the opposing force by a very, very small magnitude. All right. So that's one. Next, people, to talk what we have. Now the first law of thermodynamics. What is exactly the first law of thermodynamics? It's the law of conservation of energy. That energy is neither created nor destroyed, but it can be transformed from one form to another form. So there are various different ways you can put up the first law. And for first law, people, we have the expression delta U is equal to Q plus W. Delta U, change in internal energy. So with respect to numericals, keep in mind delta U, Q and W, all three should be in the same units. joules or kilojoules or cals or kilocals. Delta U, change in internal energy. Q, amount of heat absorbed or evolved. And W is the work done. And for W, we have two formulas that what we will see next. One is of PV type of work, where W can be minus P external delta V, or W can be W max if it is isothermal and reversible process. Now the sign conventions, minus W, matlab work done is negative. So work is done by the system on the surrounding. The piston displaces upward, the gas will expand. Plus W, work of compression. Work is done by the surroundings on the system, the piston goes down. Plus Q and minus Q are easy. Plus Q, heat is absorbed, that's endothermic. Minus Q, heat is evolved, that's exothermic. And plus delta U, that's increase, and minus delta U is a decrease in internal energy. So that's the first part. Then we have the corollary and the modified one. Now come to maximum work. What's maximum work? As I said, two conditions for maximum work. That's isothermal and reversible. So the formula for W max here, minus 2.303 nRT log of V2 by V1 or P1 by P2. V2 by V1 or P1 by P2 is with respect to Boyle's law, where at constant temperature, pressure is inversely proportional to volume. So either V2 by V1 or P1 by P2. Alright. Once again here, unit of R is unit of W max. So if R is in joules, W max is also in joules. Alright. N is the number of moles, that's given mass upon molar mass. For W max, two words, isothermal, reversible. Second one we have, that's called PV type of work. Now PV, that's work done at constant external pressure. There's a change in the volume. So that work is called minus P external delta V. Important to note, pressure is never negative. So minus P external delta V, don't take negative sign. Negative sign is for what? When work is done, the system is losing some amount of its own internal energy. So if it loses, we don't show anywhere in the expression. To express that, we put a negative sign. So W is minus P external delta V. Two forms to understand now. Quick, plus W minus W, what I just said. If P external pressure is positive, always positive, V2 is greater than V1, so delta V is positive. P external delta V is positive, but work done will be taken negative, work of expansion. On the other hand, P external always positive. Now if V2 is less than V1, delta V is negative. Whole expression P delta V is negative, work done will be positive, that's minus of minus P external delta V. Alright, that's one. Then comes internal energy. What exactly is internal energy? Internal energy is the energy stored within a substance by virtue of its kinetic and potential energy. Kinetic energy of four types, depending upon the what we call as the physical state of the substance as solid, liquid or gas. Translational, rotational, vibrational and electronic energy. And potential energy of two types, intermole energy and intramole energy. Okay, that's one. So this is the whole part. Delta U, change in internal energy, vibrational, rotational, translational, electronic, intermole and intramole. What's inter and intramole? Those are the two forms of potential energy. Okay, intermole, between two molecules, intramole, between two atoms within a molecule, then that's called intramole. So intra, within, inter, between. Then we have next periodic function to talk, people, that's enthalpy. What is enthalpy? The heat content of a substance, amount of heat which is stored in a substance, that's called enthalpy. Enthalpy also a state function and it is an extensive property, depends on the amount of substance present. Expression for enthalpy, H is equal to U plus PV. So it's a combination of internal energy U plus PV, that is the energy due to its pressure and volume. Alright, that's one. And if I do can we measure the absolute value of enthalpy? No, but we can always determine the change in enthalpy. So we have an expression for enthalpy change, delta H is equal to delta U plus P delta V. And if I talk for an ideal gas, then P delta V can also be written as delta nRT. So if I substitute P delta V as delta nRT, the expression becomes delta H is equal to delta U plus delta nRT, where what is delta N? Difference in the number of moles of gaseous products and gaseous reactants. What about solids or liquids? You will not count for them. It's only for gaseous products and gaseous reactants, because P delta V is delta nRT only and only for an ideal gas. All right, that's one. So these are the expressions we have. One is for enthalpy change, one is for delta H is delta U plus delta nRT, and we discussed QP is delta H, QV is delta U. So we can have this expression also. All right. There are many MCQs with respect to delta H greater than delta U or delta H less than. Then very simple. These are the terms. If delta N is positive, delta nRT is positive. So delta H is greater than delta U by delta nRT amount. If delta N is negative, then delta H will be less than delta U by delta nRT amount. And if delta N is 0, meaning gaseous product is equal to gaseous reactant, so delta nRT is 0. So in that case, delta H is equal to delta U. Then next, people work done. Suppose I want to know what is the work done in a chemical reaction. Now chemical reaction we just now did, P delta V is delta nRT, but again it will be with a negative sign. So this is the expression there. Anybody can see, please. That is the work done in a chemical reaction, where work done will be minus delta nRT. That's one. Now the next part we have, people, that's thermochemistry. That is the different types of reactions. What is thermochemistry? Amount of heat changes or the enthalpy changes taking place in a chemical reaction. We know two types of reaction, exothermic, endothermic. Exo, out, heat is evolved, given out to the surroundings. It's a mountain going down for exothermic. Enthalpy of the product is less than the enthalpy of reactants. So products are more stable at low temperature. Endothermic, a mountain going up. Products enthalpy is more than the enthalpy of the reactant. So products are more stable only at a very high temperature. That's one. Now we have something called delta H. We just now discussed, that's called heat of reaction, amount of heat exchange. Now if we have all formation values, now these are the different types of heats of reaction, what we will be saying next. In that delta HF, enthalpy of formation, what does that mean? 1 mole of a product is formed from its constituent elements. So if all formation values, listen to this very carefully, these are the tricks involved. If enthalpies of formation is given of reactants and products, then delta H will be summation of all the enthalpies of the products minus summation of all enthalpies of reactants. That's this formula, delta H. When all formation values are given, keep in mind this variable, formation, okay? Now, thermochemical equation mein we will see the different types. Isme first one we have, see here, heat of combustion, delta HC. What's enthalpy of combustion? Enthalpy of combustion will be defined as when 1 mole of a reactant burns with excess of oxygen to form its respective oxides. So if it's a hydrocarbon, oxide of carbon with excess oxygen, carbon dioxide, hydrogen oxide, water. Generally for hydrocarbons it's CO2 and water, but depending upon compound to compound, it will form its oxides. And most important, whenever you have to frame an equation, is this clear for numericals for delta HC? One trick to remember, the reactant is always 1 mole which burns with excess of oxygen to form the product, that is its oxides. So never balance the reactant. Reactant is always 1 mole. Dusra, delta H value for combustion is always negative. That's one. And one more trick now with respect to MCQs. If all formation values were given, what was the formula on the previous page? I said delta H is summation of enthalpies of products minus reactants. But if all combustion values are given of reactants and products, then delta H will be summation of all the combustion values of reactants minus summation of all combustion values of products. So for formation, products minus reactant. For all combustion values, reactants minus products. Clear? And look at this value of delta H. Now second one we have enthalpy of formation. Formation, people, how you do? Delta H naught F. product formed is always 1 mole from its constituent elements. So write the product first and then looking at it, put the elements over there. That's enthalpy of formation. So these equations are actually algebraic equations. Is this clear? You can play with these reactions, what we'll be seeing in Hesss Law. So whenever you frame equation of formation, rule simple, product is 1 mole from its constituent elements and delta H value for formation may be positive or negative. Matlab enthalpy change may be exothermic or it may be endothermic. Second point, for combustion delta H is always negative, means it's always exothermic. Next comes people another important heat to discuss, heat of neutralization. What is neutralization? Basically acid plus base giving us salt and water. So are the molecular weights reacting? No, it's not the molecular weight, it is their gram equivalents. What's 1 gram equivalent? The equivalent weight of the substance is called 1 gram equivalent. So when 1 gram equivalent of an acid combines with 1 gram equivalent of a base, then that heat liberated, because it's always exothermic, is called enthalpy of neutralization. We have 4 types of salts. Salt of strong acid, strong base, where the enthalpy of neutralization will be maximum because H plus and OH will be neutralized completely. Why? Because strong acid and strong base ionize completely. Here what is the heat liberated? ये value आपको याद रखनी है. Minus 57.32 kilojoules per gram equivalent or minus 13.7 kilocals per gram equivalent. Always exothermic. Achha, what about the remaining 3 salts? Like salt of when you mix strong acid, weak base, strong base, weak acid, weak base, enthalpy of neutralization will always be less than 57.32. Why? Because in this category, strong acid, weak base, you have a weak base. Strong base, weak acid, you have a weak acid. Weak acid, weak base, both acid and base are weak. All weak acid, weak base we have done in ionic equilibrium में सबने किया हुआ है. They ionize to an extent of 5%. So if they ionize, they need heat. So they will take it from where? From whatever is from the solution itself. So they say a part of the heat is absorbed and the rest is evolved, because ionization of the weak acid or the weak base is always an endothermic process. So you will see for strong acid, weak base, strong base, weak acid, weak base, enthalpy of neutralization value will always be less than 57.32. Alright, example, strong acid, strong base value is minus 57.32. For strong acid, weak base, is this clear? Like say NH4Cl, you have a weak base, ammonium hydroxide. Suppose the enthalpy of neutralization is only 40 kilojoules per gram equivalent. So it should have liberated 57, it liberated only 40. So what about the balance 17.3? That much is absorbed by whom? By the weak part. Who's the weak part? NH4OH for its ionization. Clear? That's one. So these 2 values you have to memorize. Now different types of enthalpies. Enthalpy of fusion. Fusion is for what, people? 1 mole of a solid is converted to 1 mole of a liquid. That's standard. H naught corresponds to standard enthalpy change. That is at a temperature of a room temperature to talk over there, as well as we have to talk in terms of what we call a standard pressure of 1 atmosphere. Then enthalpy of vaporization, that's for 1 mole of a liquid to gas. Enthalpy of sublimation, straight away solid to gas, like camphor, iodine, they sublime. Enthalpy of ionization, people, are to form its ions. So basically a shortcut, sublimation is fusion plus vaporization. That is sublimation. Ionization, people, we have all done in periodic table. Third I is always greater than the second, which is greater than the first, because as we go on removing an electron, what will happen, people? Nuclear charge goes on increasing. So, but obvious, I value will increase. IE and EG, ionization enthalpy and electron gain enthalpy, are opposites. Why? Ionization enthalpy is the energy supplied to remove the electron. So delta H is positive. Delta H EG, electron gain enthalpy, is the energy released when an extra electron is added. So that's why it's opposites. That's one. Then next we have, people, different enthalpy of atomization, that is to break down to form its free atoms. Now it says next we have enthalpy of solution. Enthalpy of solution, that is a substance when dissolved in a specific amount of a solvent. Is this clear? Then the amount of heat that is exchanged when a solute is dissolved in a solvent is called enthalpy of solution. That depends upon three forces: solute-solute, solvent-solvent, and solute-solvent interaction. And for ionic compounds, the energy responsible for holding the cations and anions together is called lattice energy. So we say enthalpy of solution is nothing but lattice energy plus its hydration enthalpy. So lattice, that is the solute-solute interaction, hydration when dissolved in water. So we can say the summing up of two. If lattice energy is strong, then that substance will be less soluble in water. But if the solute-solvent interaction is stronger, then but obvious, we will say the substance will be more soluble. So its hydration enthalpy will be greater. That's one. Next we have the Born-Haber cycle. This we have done in Nature of Chemical Bond also. Formation of NaCl. Sodium in the solid state first goes to sodium in the gaseous state, that's sublimation. Gaseous state, it loses electron, so that's ionization enthalpy. Third, we have chlorine break down to form chlorine atoms, that's enthalpy of atomization. The same chlorine atom will gain electron to form Cl minus, that's electron gain enthalpy. And Na plus and Cl minus, the attraction is called lattice energy, and all of this together gives us enthalpy of formation of NaCl. So formation of NaCl is a summation of 5 energies: sublimation, second is ionization, atomization of chlorine, electron gain enthalpy of chlorine, and lattice energy of NaCl. So that's the formula we have for formation of NaCl. Numericals also the same way. They will give you all the variables except one. You find the one which is over there. Like for example, in this, lattice energy is to be found. That's one. Next is enthalpy of dilution, people. That is when we say a solution of a known concentration is diluted to a solution of another concentration. That's called enthalpy of dilution. Then we have Hess's law. What is Hess's law? It's basically constant heat summation, amount of heat exchanged in a chemical reaction. If the reaction takes place in one step or in multiple steps, the net enthalpy change will always remain the same. So Hess's law is basically nothing but law of conservation of energy, and according to Hess's law, delta H enthalpy change is a state function. Its value will only depend on its initial state and final state. So whether I take the reaction directly, see the diagram, A to D only in one step, that's delta H1, or I take A to D with delta H2, delta H3, or delta H4. If I add all of them, so that's what the final expression is. Delta H1 will be equal to 2 plus 3 plus 4 over there. So in how many ever steps are there, finally the enthalpy change will remain the same. In numericals on Hess's law, important framing equation. Formation, product is 1 mole from its constituent elements. Combustion, 1 mole of reactant burns with excess of oxygen to form its oxides. Play with the equations in such a way, all these thermochemical equations, formation, combustion, neutralization and all, they are algebraic equations. You can do all mathematical operations. Depending upon your required thermochemical equation, you may multiply them, you may divide them. Third, important, never subtract. Rather than subtracting, an easy trick, reverse it. When you reverse, reactants become products, products become reactants, and value of delta H will also change. Positive value will become negative and vice versa. And finally, whatever operation you have carried out, whether it's multiplying the equations, dividing it, reversing it, finally we add all to get the net enthalpy change. That's Hess's law. Next, people, heat capacity, Cp, the heat capacity at constant pressure, Cv, heat capacity at constant volume. We just now did Cp was change in enthalpy. So for a very small change, Cp will be dH by dt, and for n moles of a gas, we can call it as nothing but n into delta H by delta T. So we have the expression for delta H and delta U. So delta H is Cp into delta T, and if it is that's for 1 mole, for n moles it will be multiplied by n, and same way delta U will be Cv into delta T. Then we have Mayer's relationship, Cp minus Cv is R. This can be explained from enthalpy change expression. Delta H is delta U plus P delta V, where instead of P delta V, we can have it as delta nRT and then equate it and with respect to the limits and get the answer. Cp minus Cv is R, where R is the molar gas constant. Then one more expression to talk, people, that is Kirchhoffs equation. This is an extra part, people, but for your information you need to know this. What is Kirchhoff equation? Rate of change of enthalpy with respect to temperature, meaning at temperature T1 enthalpy change is delta H1. So at temperature T2 you will have a new enthalpy change, delta H2, and this change will depend upon the delta Cp value, which is nothing but the heat capacities at constant pressure or at constant volumes. So we have the expression delta H2 is delta H1 plus delta Cp T2 minus T1, where delta Cp will be Cp of products minus Cp of reactant, which is always for 1 mole. Depending on your equation you can use. And same way we can also have rate of change of internal energy, that is delta U2 is U1 plus delta Cv T2 minus T1 at constant volume, where delta Cv will be Cv of products minus Cv of reactants. That's one. That's Kirchhoffs law. Then now, people, we are going to talk about the second law and the third law. First law has limitations. What is that? It only tells you that energy is neither created nor destroyed. It's only transformed, but is not talking about the direction. So direction has to be specified again, in which direction the heat is flowing. To explain that, we have to talk about spontaneity. What is the meaning of this word spontaneous process? Process which takes place on its own, doesn't require any external aid. So a process taking place on its own is a spontaneous process. Now what are the factors? One factor is enthalpy factor, that is delta H, which could be positive for endothermic, negative for exothermic, that's delta H. Second factor, we have randomness factor. Randomness factor, a new thermodynamic function, entropy change, or entropy what we call, where we say more the gaseous, if the gaseous products are more than the gaseous reactants, then randomness is more. We can also have like hydrogen gas splitting to give 2 hydrogen atoms. Then also we will say the randomness will be more with respect to what we have as nothing but hydrogen atoms will have more randomness as compared to hydrogen molecule. Then, so these are the part what we have. Then we also have a driving force. The driving force, it is clear, which also makes the process spontaneous. Then randomness, people, different factors, that is the physical state, more gaseous substance, more the randomness. Temperature, people, but obviously on increasing temperature the kinetic energy will increase. Then the pressure, yes, at low pressures we will say randomness will be more. Complexity, people, that's because of the rotations, that's because of the vibrations taking place. Dissolutions, then chemical decompositions, and we have an expression for delta S. Delta S is summation of entropy of products minus summation of entropies of reactant. Now the expressions you have to see carefully. Delta S is the heat exchange reversibly over a given temperature, but for a system Q reversible is enthalpy change. So the formula becomes delta H of the system by temperature. And what will be for surrounding? Minus delta H of the system upon T. Because whatever heat is given by the system, or sorry, whatever heat is lost by the system, that much is gained by the surroundings. So that's one variable we have. Then the second law in a different way, that the total entropy of the system and the surrounding increases in a spontaneous process. That's the second law. And we have 3 variables to talk. Delta S total, that is delta S of system plus delta S of surrounding. If delta S total is positive or is more than 0, then the process is spontaneous. If delta S total is negative, then the process is non-spontaneous. And if delta S total is 0, means the process is in equilibrium. So delta S formula, delta S total, that is equal to delta S of the system plus delta S of surrounding. Dusra, we can talk about nothing but delta S for a system will be delta H of the system upon the temperature. So delta S and T are inversely proportional. Same way for delta S of surrounding, it will be minus delta H of the system upon T. That's one. So that's about we have as delta, this entropy of the system. Next factor we have, that's the last part, that is Gibbs energy. What is Gibbs energy? amount of free energy which is present within a system which can be used to do useful work. That is called free energy. Now for free energy, people, the expression, look at that. G is equal to H minus Ts, where H is enthalpy, T is temperature, S is entropy. So G can, H we all know, H is written as U plus PV, enthalpy ka expression. So G can be written as U plus PV minus Ts. So Gibbs free energy change we have, that is delta G is delta H minus T delta S, and for standard, delta G naught is equal to delta H naught minus T delta S naught. Now delta S of surrounding will be the Q of surrounding by T, which is minus delta H by T. So delta S total will be system plus surrounding. So if I equate both, people, what is the understanding? Delta G is minus T delta S. Now temperature is never negative. So delta G and delta S are opposites. They both have opposite sign. Okay. So which means if delta S total is more than 0, the process is spontaneous. And if delta G is less than 0, then the process is spontaneous. So for delta G, the expression goes like this. 1, delta G is delta H minus T delta S, where, important point to know, delta G less than 0, process is spontaneous. Delta G equal to 0, process is in equilibrium. Delta G greater than 0, then the process is non-spontaneous. Clear? And a spontaneous process, people, is always favored by decrease in enthalpy, matlab exothermic, because products are associated with less heat. Increase in entropy, so gaseous substance is more than gaseous reactant, and decrease in free energy. Decrease in free energy, that is, the free energy is lowered, process becomes more spontaneous. Now people, with respect to this, delta G also a formula to calculate delta G naught standard. Delta G will be delta G of the formation of the products minus delta G of reactant. This table very, very important because lot of questions on spontaneity. Simple expression, delta G is delta H minus T delta S. So if delta H is negative and delta S is positive, then at all temperature, delta G is always negative. Second, delta H positive, delta S negative, then delta G will be always positive, means the process will be non-spontaneous at all temperatures. Third, delta H negative, exothermic, delta S also negative, that is entropy decreases, then delta G will be negative, is this clear, over here, at low temperatures, is this clear? But as the temperature increases, delta G will go on increasing from negative to positive, so the reaction will be non-spontaneous at high temperature. So here people, here we will say delta G goes from negative to positive, so it becomes, here there's a mistake here, it should become non-spontaneous over here. Okay, that's one. Last variable, delta H positive, so that is endothermic. Delta S positive, matlab entropy increases over there. Here we say delta G will be negative, is this clear over there? Under what situation? At high temperature, and it will be non-spontaneous at low temperatures. So this table very, very important, right? Now entropy change for different transitions, people. For different parts, we have different thing, like say delta S of fusion. So it will be delta H of fusion over the temperature of fusion, and that's a positive value. Fusion and freezing are opposites. That's why this will be with the opposite sign of fusion. Same way sublimation, delta H of sublimation by T. Vaporization, delta H of vaporization by T. Vaporization and condensation are opposites. So condensation ka ulta will be nothing but over here delta H, or basically minus delta H of vaporization. Vaporization with a opposite sign upon temperature. Now people, entropy change delta S for an isothermal process. Isothermal process, so delta U is 0. Formula for delta S is what? Q reversible by T. Q is nothing but the, over here in this case for isothermal process, Q is the work done because delta U is 0, first law of thermodynamics. So Q is minus W. So now W is for isothermal reversible, W max. So minus minus becomes plus. So minus minus plus 2.303 nRT log of V2 by V1 upon T. So TT gets cancelled. So the formula delta S is what we have here, 2.303 nR log of V2 by V1 or P1 by P2. Everybody clear? Okay. Same way isochoric, where we say volume remains constant. So delta S is 2.303 NCV log of T2 by T1. And same way for isobaric, It'll be 2.303 n Cp log of T2 by T1. Clear? That's one. Then people, with respect to equilibrium, what will be the values over here? Because T is the temperature which changes from spontaneous to non-spontaneous and vice versa. So these are the different concepts, or the slide is based on that. So if T equilibrium is the temperature at equilibrium, there will be delta H upon delta S, because we have the formula at equilibrium. See this line please on the slide. At equilibrium, delta G will be 0. So if delta G is 0, in this expression we'll have delta H is T delta S. So T will be delta H by delta S. So that's the part. Now if we have both delta H and delta S, delta H negative and delta S positive, then temperature, then this variable will be negative over here. So in that case it is never in equilibrium. Now temperature, if one is positive and delta H is positive and delta S is negative, again the temperature is positive, which indicates it will never be in equilibrium. And here the parameter over there, what we'll say, if delta H is positive and delta S is also positive, temperature at equilibrium is positive, so reaction proceeds, the temperature T will be more than its equilibrium, then delta G is negative, the process is spontaneous. And same way, if T is less than T equilibrium, delta G will be positive, the process is non-spontaneous. And last factor, delta H negative, delta S also negative, then that temperature part has to be positive, so it will be opposite. T will be greater than T equilibrium, so delta G is negative. That's one. So high temperature favors the spontaneity of endothermic, because endothermic is favored at high temperature, and exothermic at low temperature. Next, free energy change also expression we have. Delta G is 2.303 nRT log of V2 by V1 or P1 by P2. And for Gibbs free energy change, people, we have the expression delta G naught is minus NF E or minus NF E naught of the cell. E naught of the cell, that's redox reaction, cathodic reduction minus anodic reduction. And standard free change with equilibrium constant, we have the expression, people, delta G is delta G naught plus RT ln Q. What was Q? Reaction quotient. That is, before a reaction reaches equilibrium, the products of the active masses of the products upon products of the active masses of reactants. At equilibrium, delta G is 0, not delta G naught. Delta G is 0 and Q becomes K. So the expression comes delta G naught is minus 2.303 RT log of K. And finally we have the third law, that is the entropy of a perfect crystal at absolute 0 will always be 0. Now bond energy or bond enthalpy, that is the energy supplied to break a bond. But if we have more than one bond between the two atoms, then we say we don't use the word bond energy, we use the word average bond enthalpy. That is the average energy required to break a bond. Just like methane, so there are 4 bonds, so 4 values will be there, breaking CH3 H bond, CH2H, CHH and CH, and all values divided by 4. That will give the average energy to break a CH bond. Delta H को calculate करने का one more formula with bond energies or bond enthalpy, summation of bond energies of reactants minus summation of bond energies of products. That's the formula. Okay, that's one. So total delta H, 3 formulas. With respect to formation values, products minus reactant, combustion values, reactant minus product. With respect to bond energies, reactant minus products. Then we have gamma, that is the ratio for Cp by Cv to tell us whether a gas is monoatomic, diatomic or so. So for monoatomic, the ratio is 1.66. Cp is the ratio of the heat capacities at constant pressure and constant volume. For diatomic 1.4 and for triatomic 1.3. ये values को याद रखो, ये important है. And last comes the zero law, that is when two bodies have equality in temperature with a third body, then the third body also will get the equality of the two temperatures. That's one. Then we have expression for adiabatic reversible expansion. These are the add-on formulas which will be mainly helpful with respect to the JE part. Alright, where we say Cp Cv wise, then the work done is, this is the formula, nr T2 minus T1 upon gamma minus 1. Gamma is the Cp by Cv ka ratio, n is the number of moles, r is the constant, and T2 and T1, they are the two lower and higher temperatures. Then we have resonance energy. What is resonance energy with respect to the resonating structure? That is delta H of dissociation experimental minus delta H of dissociation of calculated. So it's basically dissociation, that is to breaking into bonds, experimental minus calculated, or with respect to formation value, it's experimental minus calculated. All right, that's one. Then efficiency of a heat engine, that's the Carnot cycle. That's again an extra point with respect to the JE and the advanced part. That is eta. This is eta in the Greek nomenclature there. That is W upon Q2, where W2, where W, if you observe, is the work done, Q2 is the heat absorbed from the source, and T2 and T1 are the two temperatures. Then the different units I have given over here with respect to ergs, joules and all that. Then we have over here the calorific value, what we say. What is calorific value? The heat exchange with respect to 1 gram of a substance. Like for example, when 1 gram of a fuel is burnt, like enthalpy of combustion is of acetic acid is 900 kilojoules per mole, that's minus, so exothermic. Now acetic acid, molar mass is 60, so 900 divided by 60, so that's 15 kilojoules per gram is its calorific value. Okay, where maximum calorific value is for hydrogen, that's 150 kilojoules per gram. Then energy exchange in a bomb calorimeter, that's delta U, which is mc delta T. M is the mass, C is the specific heat, and delta T is the change in temperature. Then with respect to lattice energy, if the lattice energy is more, then the ionic compound is more stable, and greater the lattice energy, lattice enthalpy, solubility is less because the solute-solute interactions are more. Delta G is minus W. So if I say delta G as minus W max, so W max can be written by this formula. Delta G is 2.303 nRT log of V2 by V1 or log of P1 by P2. This is the gist of entire thermodynamics. I hope everybody's has just gone through it. You have just summarized or revised the part. Write down all the formulas and practice the MCQs over there. Wish you all the best. Thank you.